All right, everyone. Thanks for joining today. We're really happy to have you all here for today's webinar. Excited for this one. To honor everyone's time and so that we can get to this content, I'll go ahead and go through some logistics and some housekeeping, and then I'll turn things over to our good friend Scott Struck to introduce our topic and speakers. So first of all, please note this meeting is being recorded and we will post it to the NAWI Alliance Community website after the event. It does take us a week or two to process that recording and get that posted, but we will get that up there as soon as we can. Please note that attendees are joined in listen-only mode. This means your video and microphone will be turned off throughout the webinar. That's just to cut down on interruptions. That said, we very much do want your questions and comments, so please put those in the chat or Q&A box, and we will address those at the end of the webinar. If you're having any audio issues, we recommend trying to connect through your phone. If that doesn't work, or if you have any other technical issues, please send me a chat or send us a chat and we will help work you through those. A couple other things, please remember that we do offer cost share for your time spent with us during this webinar. I will put this link in the chat and you can do that after the webinar. Also, if you have any questions about the program, you can or about cost share, you can email us at that email on the screen. And also, you may have heard, we are going to be doing a lot of our communication moving forward through LinkedIn, and a lot of our content will be up on that page. So please follow us on LinkedIn, check us out, and stay tuned for all we have coming up. And with that, I will kick things over to Scott to introduce our topic and speakers.
Hey, thanks, Ryan. Well, good day, everyone. Appreciate you joining us. I'm pleased to be hosting the webinar today. My name is Scott Struck. I'm with the National Renewable Energy Laboratory, and I do primarily water energy nexus type of work. And I have the pleasure of working with a lot of the pilot folks that are working under NAWI, making sure that we are executing what we want there and are monitoring properly. And speaking of monitoring, today we have a great presentation from our team that's doing project 5.17. It's data-driven fault detection and process control for potable reuse with reverse osmosis. And I'm pleased to introduce our speakers that we have here today. First, we have Kate Newhart from Oregon State University. She's assistant professor in environmental engineering. And Kate takes on real-world challenges of our aging water infrastructure, leveraging big data, which of course there's a bunch of if we're doing monitoring properly. Kate is focused on data-driven process monitoring, control, and optimization of water, wastewater, and resource recovery systems. Her recent work includes prediction of carcinogens in reverse osmosis-based water reuse systems, kinetics of novel disinfectants in wastewater, and phosphorus recovery. A big topic these days for those that are pursuing resource recovery options. We also have Taylor Grimm joining us today. He's a PhD candidate in Department of Statistical Science at Baylor University. Taylor received his master's degree in statistics from Baylor in 2022 and a bachelor's in statistical science from BYU in 2021. Taylor's now not at Baylor, just finishing up stuff, but has started a new job. Congratulations, Taylor. His research in the past focused on developing and applying multivariate statistical methods to detect faults in water and wastewater treatment processes. We did have Kyle, Dr. Kyle Thompson, also on the docket today to speak from Carollo Engineers, but Kyle is not going to make it because he's receiving an award. So congratulations, Kyle, on that. But instead, we'll have Kate, we'll have you start off and introduce the topic.
All right, thank you, Scott. Thank you, everyone, for joining us today. Like mentioned, my name is Dr. Kate Newhart out of Oregon State, and I'm going to be presenting the phase 1 results from project 5.17. I'm going to start off with a brief introduction to the project team, and then Taylor and I will be presenting the results from our pieces of the project. So project is largely led by Carollo Engineers, but we have some great utility partners. So Las Virgenes Municipal Water District, West Basin, and Orange County, right? So we have that Southern California reverse osmosis reliant potable reuse trains, as you can see, and they have been fantastic utility partners for this project, presenting their expertise and their challenges and their data. The remaining measures of the project team include the academic side of the house, so Baylor University, led by Dr. Amanda Herring of statistical science, and also industrial. So Yokogawa is a process control company out of Japan, and NWRI as an advisory component for our work to keep it grounded. So a very large project with large interdisciplinary teams across expertise and across roles. A quick introduction to potable reuse. So while many NAWI projects are looking at industrial streams, we're focusing on the municipal side of the house, because obviously as we have people generating waste, they're also generating demand. So it's a very important water supply option in the present and moving forward. So potable reuse in the United States is expected to double or triple depending on the region within the next 10 years. So for example, the upgrade project at LA Sands Hyper-Ion wastewater treatment plant will make it the largest water reuse facility in the world. However, in contrast to LA Sand, many of the anticipated reuse facilities in the next 10 years will actually be smaller facilities, so less than 1 MGD. So as we think about the challenges to potable reuse within the next 10 years, it's going to be ways that we can guarantee quality, identifying good ways to regulate, monitor, and control in the face of limited staff and limited resources. So this project, like I mentioned, is focusing on RO-based treatment trains like the one presented on the top there. And for those trains, we have 2 tracks. So we are attacking the fault detection challenge and the process control challenge of these RO-based treatment trains. So fault detection, obviously, if we talk about limited staff, any amount of time that you can give for proactive response to changes in water quality, changes in processes is important. And then optimizing process control, as now we're talking about regulatory limits that are much more stringent, and mechanistic modeling, or the fundamental understanding of the processes, is no longer going to help us improve the process control or the on the ground aspect of, you know, the brick and mortar and the pumps that are operating. So of our project, the first phase, or year 1, was based on desktop simulations across 3 different fault detection approaches and 2 different process control approaches. For fault detection tasks, we looked at items like, could we get fewer false alarms or a faster response time? And for process control, we looked at, in our simulation, could we find a way to reduce energy consumption or embedded costs? So we've just completed year 1 desktop modeling, and we're moving into year 2. Obviously, those sampling campaigns are currently ongoing, and I'll talk a little bit about that at the end. But today, we're going to be talking about our tasks 1.2 and 1.4, so for a fault detection and process control. And with that, I am going to pass it off to Taylor to present his work.
All right, thanks, Kate. I'm going to pull up my slides real quick. Okay, so yeah, like Kate said, part of this project is on fault detection. So I'm going to be talking about what we did for building a data-driven fault detection model for some data from this pure water project that I'll talk about in a minute. On this project, it was me working with Dr. Amanda Herring from Baylor and then Dr. Kate Newhart. And so basically for this project, we have this facility where we're interested in, trying to help them figure out how we can use all of the data that they're constantly getting from various sensors and so on to determine if, there's faults in the process, or if we're seeing abnormal behavior. So the data that we have is from this pure water demonstration facility. It's this demonstration facility in Southern California that consists of this advanced treatment process. We can see a picture of it here, where we have this ultrafiltration portion followed by reverse osmosis and then UV AOP. For our specific project, we focused on just looking at the beginning portion of this with the ultrafiltration, data and how we can, build a model to ideally detect in real time whether or not there's a fault in the process. So we have a lot of different variables that we have data for from this facility. We had data over a little over a 2-year time span, and we ended up taking all this data that I have listed on the right and obtaining 15-minute averages of it. And so that's what we used to build our model. The variables that we got, that we have data for, we decided to split into kind of 2 categories that are shown here. So the first category of monitoring variables here on the right is kind of motivated by what our actual goals were for detecting faults in this process. So, what types of faults are we trying to look for? So the first type that we decided was, okay, we wanted to be able to detect whether we have membrane fouling or not. So for that goal, we've associated it with monitoring temperature corrected permeability. And then similarly, we wanted to monitor filtrate quality and upstream quality, which are associated with the filtrate turbidity and ammonia values. So those are kind of our 3 primary variables of interest that we're trying to, detect changes in. But then we have all this other data from these explanatory variables. So we don't want to just throw that out because there may be useful information in those variables. So I'll talk in a minute about how we use these, what we've termed explanatory variables, to help us with detecting faults in the other variables in the process. So the general approach that we take is in this class of methods called statistical process monitoring. So this is a data-driven approach where we can detect faults in real time. So the way we do it essentially is shown here. We take a set of data called our training data that is, historical data where we've observed over some period of time everything in the process appears to be in control and, under normal operating conditions, and nothing, abnormal is going on. And then during our testing period, or after that, we can take in new data and compare it essentially to what we saw in the training data. And then we can use that to build a model to kind of classify each new observation as in control or out of control. Is everything behaving as we saw or as we should see under normal operating conditions, or is there a fault? So here's a simple example of how we could do this for a single variable. So imagine, one of our variables is filtrate turbidity, for example. Imagine we have here over time, we're plotting a value of filtrate turbidity, and we have these upper and lower limits where if we go, outside of these bounds, then we'd say that something abnormal is going on, and we'd flag that observation as a fault at that point in time. But if we're between those limits, then we'd say that everything's fine. So this is a simple example of how you could do it for a single variable. But remember, we have more than one variable that we're interested in. So we can use a multivariate approach that kind of works similarly, except we take all the information. For example, if we have 5 variables, we can take the information from those 5 variables, we can condense it down into a single statistic that is then plotted over time. And so we can use a statistic computed from all the original information to represent deviations in the means of a variable or the covariances or, the relationships between the variables. And then we can plot that over time as a condensed measure of what's going on. And everything else is similar to before. We observe behavior during this in control training period. And then what we do is we set an upper limit or threshold that will tell us whether or not an observation will be classified as in control. So basically, we take new observations during this testing set, and we just compute the statistic at each point in time and then compare it to that threshold. And if it's above, then we say the process is out of control. And if it's underneath, then we'll say the process is in control. So for this specific application on the pure water demonstration facility data, we have kind of 3 main parts that we had to tackle. The first was we have all this data over a couple of years, but we don't have any idea of where the in control training data is that we can use. So we kind of had to go sift through that data to find a training period that's clean, has no faults, and it's all representative kind of normal operating conditions. So that's the first challenge. The next is the actual model building portion. So we have to be able to take all the data that we have and build a model that will tell us whether we have the process is, abnormal at some point in time. So the way that we're going to, and we also want to make sure that that model accounts for natural changes over time, so we can apply it not just over, a week or a couple days at a time, but we can also apply it over a long period of time, like a year or more. So that's another thing to consider in model building. And then we also want to account for those explanatory variables and not only use those monitoring variables that I talked about. And then finally, we have to evaluate how the model performed, which is difficult also in this case because the facility, to our knowledge, has no existing method for automated data-driven fault detection. So we had to kind of come up with a baseline for comparison. So for the first part of this, selecting training data, basically what we did was we built this little app that lets us select any variables that we want to look at in our data set, and we can kind of narrow in or out on different time frames. And what we looked for was periods of time where we had at least several days, ideally a couple weeks, of stable behavior with no obvious faults. And then we also wanted to see periods of time where we shortly after that had an obvious fault or a change occurring, so that when we build our model, we'd be able to test, okay, are we able to detect this obvious shift that we should be detecting as kind of a sanity check before we go along for further testing. So that's how we identified our training data. So we ended up picking out 2 time periods that we used for some short-term, like 2 to 3 week long case studies to help us with our model selection. Next was actually building the model. So we took a 2-step approach to building our model. The first step was what we call detrending. So this is where we take those 3 monitoring variables of interest. We had our temperature corrected permeability, our filtrate ammonia, and our filtrate turbidity. And then we wanted to remove any effects of the other variables on those. So essentially, we wanted to use a model that will, after we're done with it, we're only left with data that tells us what was going on in the process that was not expected based on all the data that we had from the other variables. So we took our data, we put it through a model, and it gives us fitted values or predictions of what the model thinks we should be seeing in each of these monitoring variables. And then we ended up with residuals where we find the difference between what we actually saw and what the model thinks we should have seen. And that's what we end up using in our fault detection model. So again, these residuals are representing unexplained variability in the turbidity or the ammonia or the permeability. We looked at several different models. I won't go into the details of these models, but some of these are some more advanced machine learning models and some are simpler statistical models. And then we kind of compared these, optimized each one individually, and compared them to find which one would work best for our application. And then once we had decided which one of those models we'd use, we built the actual fault detection model itself, where we take those residuals or the unexplained variability in the process, and then we pass it through this adaptive dynamic principal component analysis model, or ADPCA, which allows us to adapt to changes over time automatically, which is nice. And it also lets us account for dynamics in the process, or we can use values of variables 15, 30, 45 minutes in the past that may help us predict what's going on now or in the future. So the way that model actually works remember we want to take the data and we want to condense it down into just one or two statistics that we can then monitor over time so that we don't have to worry about all the variables individually. So we take those residuals from that detrending model, and we can imagine that that's what these are here, A and B in this plot on the right. This kind of represents, this is like a 3D plot. So you can imagine in one dimension, you can plot the permeability, in another you have turbidity, in another you have ammonia, and that gives you a point in space like A. And when we apply this adaptive dynamic PCA model, what we're doing is we're kind of squishing this down from the original 3-dimensional space to, in this image, a 2-dimensional space. So we're like compressing the data in a sense. And that allows us to compute these two statistics that are pretty nice. The first one is t-squared, which essentially tells us, after we've applied this model, we now have this point that's squished down onto this surface. How far is this point from the average of all of the points? So basically, how different is the observation that I'm looking at right now from everything else? So that's what t-squared measures. And then we have SPE, or squared prediction error, which measures basically how far is our original data point from this squished down data point after applying this model. So it tells us kind of how good does this model fit, or mathematically, it will tell us if there's changes in the relationships between the variables in the process. So these are kind of two measures that we're able to get from applying this model, that we can now track these two variables or these two statistics over time to detect whether or not there's a fault in the process. So this is an overview of the whole process and how it works, from training to testing. And I've already talked about all this. So basically the flow, it goes like this. We start with our initial clean training data set. We estimate our detrending model. We estimate this PCA model. We compute our statistics for that initial set of data to estimate what the upper limits should be, or the thresholds for classifying in control or out of control. And then as we take in new observations, we just pass them through the same models to get our t-squared and SPE statistics for each new point in time. And then we just compare it to that upper limit. And if it's above that upper limit, then we're going to say, okay, this is a fault, process is out of control. We may need to look into, what's going on. If not, we'll say it's in control. And then we just repeat this training and testing process as we get it, receive new data, basically, so we can make sure that it stays updated with changes that happen naturally over time. So this is what the actual kind of evaluation of the model looked like when we applied it to data over a long period of time. So we had our initial training set where we trained our models, and then we have this black period between April and May in 2021 and 2022 that kind of represents just a long period of time where we didn't specifically go in and see whether or not there were faults in the process. We just kind of want to see what the model is going to tell us. As with any process, we would expect that there'd be some periods of time where there's a fault, but ideally, most of the time, everything should be, running smoothly without any major problems. So that's what we'd want to see happen from our model during this time period. And then we have two time periods that we know are in control. So the model should specify it as in control. And then a period of time that we know is out of control because we've gone in and looked at the data and we saw that there's a fault. So that kind of gives us guidelines of, when we apply our model, we should see that, this period of time is going to be classified as in control, and this period of time should be classified as out of control. So we compare our model with the approach that I described initially, where we just take those three monitoring variables and make just upper and lower limits for each of those separately. So we're going to see how our model does compared to that simpler approach. So one of the things that's important to do with the model that we built is you kind of have to adapt it based on the data set and the time span that you're looking at. And we found that, you know, we have to adjust how big is our training window, or how many observations, how many days worth of data are we using to train it over time. And so we looked at, if we just use a little bit of data to train it initially, we had some problems where basically we see here, here we're plotting these monitoring statistics on the top and bottom for this process over time. And whenever these values are above this red line, it means that we're saying that there's a fault in the process. So essentially, this specific configuration of the model is saying that the entire process over this year-long period is all out of control all the time, which is not right. So there are some kind of things that we had to tweak in the model, some parameters of how it was constructed. And we ended up with this one on the right. And this one on the right gives us more of what we expected to see. So we can kind of see as we go through time, there are periods where these statistics are above this red line, which means that we're saying there's a fault during that period of time, but then it falls back underneath, and it kind of alternates over time based on what it determines to be in control and out of control. And then at the end, we see that we have this period of time that's blue that we identified, that we knew manually looking at the data should be in control. And it's pretty much being classified as in control by our model, which is good. And then this final portion where we have a known fault occurring, we can see it spike back up. And so that kind of is a sanity check that the model is, you know, a year later performing as we expected it to, which gives us confidence in kind of these other things that are being identified along the way. So if we look at the simpler comparison where we just build a separate little plot for each of those three variables, we ended up seeing a problem where either just a lot of stuff is randomly getting flagged as out of control, like we see here, or down here, pretty much everything is being classified as out of control during the entire time period. Over here, it's a little bit better. At the end of the time period, we're kind of correctly classifying things as we wanted to, but it's still not ideal. So overall, basically what we saw from this project was it is possible to build a model that will let us, you know, automate long-term fault detection with data. And we did find that we improved performance when we used a detrending model. Here we did not have a ton of variables we were working with. So we had 3 primary monitoring variables and then about a dozen or so explanatory variables. But this method becomes increasingly useful if we have more and more variables we're wanting to monitor, because you still only get the same output of 2 plots that you're looking at over time, which simplifies things a lot. We had to do a little bit of tuning to make the model work as expected, but it ended up working pretty well. So that kind of summarizes this major project. Some additional work that we have that we've done more recently than this project was part of this project enhancement grant, where basically we found that when working with real life data from these different facilities, it's really hard to find a nice clean historical set that we can use to train a model. Or, you know, in some cases we may have a new process, so we don't really have very much historical data. And, you know, if we do have historical data, it might have a lot of sensor issues or contamination in data. So we wanted to look into methods that we can use when we have these problems. So we ended up coming across self-starting methods, which allow you to monitor processes with minimal historical data, and then robust methods that let you monitor processes when you do have data, but it's contaminated or there's, you know, problems in the data. So those are kind of things that we ended up or have been looking into as part of this project enhancement grant, where we're investigating existing methods. And then we also have developed a new method that I won't show here that shows promise in kind of combining these, where maybe we have minimal historical data and it's contaminated. So how do we monitor that type of data? So that's kind of recent developments that we've been working on that is an extension of this work. But yeah, that kind of summarizes this. So I think we'll do questions at the end, but I'll turn the time back over to Kate to talk about her work.
Thank you, Taylor. Yes, you will be seeing the results of the robust self-starting method as they finish. Taylor is defending his PhD here in about a month. So we're working on getting that work wrapped up as well. So I am going to be shifting gears now to the process control side of the house. And specifically, we're monitoring the post-RO. So what is the NDMA in the post-RO? And we're going to use that as a soft sensor. And so really briefly, I want to introduce you if you don't know what the concept of a soft sensor is. So if you think about monitoring a constituent like ammonia, right? We have an ammonia sensor, right? There's a physical piece of hardware that we can put in the system to measure ammonia or to approximate what the real-time ammonia is. So if that is a hardware sensor, the analogous for a software sensor would be using a model instead of a piece of hardware to estimate the real-time ammonia. And this model could be many different types of models. And the crux of it is that it takes data from other parts of the plant. This could be ammonia measured elsewhere. This could be flows, pHs, ORPs, any other data that we have available to capture the variability in ammonia. So when would we want to use a soft sensor? Well, the biggest criteria, the number one is the analyte difficult to measure in real time? So this could be an analyte that is only available in the lab, right? So the technology does not exist yet for real time or is not commercially available. The analyzer that might be available is extremely cost prohibitive for small to medium-sized facilities that maybe can't afford the lab staff to maintain it or the continuous, purchase of reagents. Or, right, if we're talking about a sensor, sensors also need a lot of maintenance, and maybe the operations staff can't attend to all of the sensors that would need to be used for the direct control, right? So if you check the box on number one, now we have to answer the question for number two, which is the variability of that analyte captured in other data sources, right? So these could be flows, other water quality sensors and analyzers, or very frequent lab samples if we're talking about real-time implementation. So what type of models can we use? Well, there's mechanistic models, right? So this is based on our fundamental understanding of biology, chemistry, fluid dynamics, physics. Here's an example here where we have CT or disinfection dose versus E. coli removal. And that red line is our understanding when you consider microbial disinfection kinetics of what the E. coli inactivation should be. And when you compare that with the full scale data, those are all those blue dots, it captures that shape really well, but does it capture it well enough to use this for real-time control? I mean, just as you look like you're getting over the hump there, the variation is just too great. So while it gives us a mechanistic insight into what is happening, it does not identify all of the possible variability or changes that can occur in our output variables. So another data-driven option would be using statistical models. So like mechanistic models, you are explicitly defining what the form of the model is, right? So if it's a linear regression, right, that's a linear relationship between the inputs and the outputs, right? Polynomial, exponential, the list goes on and on. These models are great because they are easy to program. They are interpretable, right? So that coefficient, the slope in my plot here between chemical dose and contaminant removal, that has physical meaning. I can compare it across systems, but it requires that my variability meet those forms, but also that my data have certain properties that are not always upheld. And one of the other strengths of statistical models, right, is the ability to have uncertainty estimates But if those assumptions aren't held, those uncertainty estimates, so my confidence intervals don't hold. So the question is, does the process meet those criteria? And is the model sufficiently flexible so that I can capture that variation that I want across the range of values that I want? So the next and final option I'll be presenting on today is machine learning models. So machine learning very broadly tries to mimic the output, right, given a range of inputs. And unlike a statistical model where I'm explicitly defining the shape and the relationship, the architecture of machine learning models is such that it's so flexible that it can fit to almost anything, right? And there's lots of different types. You know, I just showed two here, the neural network style and the ensemble or decision tree style of machine learning models. But the emphasis that I want to place here is that there is no single machine learning architecture that is universally better for environmental engineering applications, such as water treatment. Rather, it takes exploring different types and configurations and parameter sets of all of these in order to identify the best for your application. And so that being said, let's dive into the case study that we're working on for this NAWI task, and that is trying to predict NDMA in the RO effluent. So here is our potable reuse system. So this is the Orange County Water District's groundwater replenishment system, where we take secondary treated wastewater. It goes through MFUF, then RO, then ultraviolet advanced oxidation processes prior to discharge into injection wells or percolation basins. We have an indirect potable reuse train here. NDMA enters, or NDMA precursors enter through the municipal wastewater, and reverse osmosis is able to remove NDMA about 30 to 50%. It varies. And that's why we need the UV system in order to guarantee removal of NDMA. The problem with that is that the NDMA concentrations, like many constituents in municipal wastewater, vary throughout the day, day to day, week to week, season to season. There is no commercially available analytical technology in order to measure the NDMA coming out of RO, right, which has inconsistent removal. So when we try to say, I need to have this UV dose in order to remove my NDMA, I basically end up assuming what is my worst case scenario. So I end up spending a lot of energy to zap my water with enough power in order to inactivate the NDMA, assuming the highest concentration that I have seen or could potentially see. So our objective here is, can I predict NDMA in the RO effluent? So this means predicting what is coming into the plant and the removal through the RO in order to better guide what my UV dose should be. So here is the data set that we are using. Orange County has an on-site LCMS, and they took three large sampling campaigns. So you can see here we have some data from September, October, and November. And the data was spaced every 3 hours. And we have about 7 to 9 days stretch for each period of time. So in total, that gives us 162 NDMA samples in the RO permeate. Now, the problem is that I have 7 water quality variables in the upstream MFUF system. So these are things like pH, flows, conductivity, turbidities, chlorine concentrations. And the RO process, right, where we have banks and stages of many, many RO units, we have 201 different process variables that are currently being monitored. So if we think about even statistical models, you need to have fewer variables than you do data points that you're training on. So how do we reduce the number of process variables so we can successfully model NDMA in this case? And this applies to a lot of RO system modeling, right? So we tried 2 different approaches. One is a correlation-based approach, and one is a projection-based approach. So the correlation metric we used was called MRMR. The projection-based approach was PCA. And the difference between the two is that MRMR is going to look for which variable is correlated to the NDMA concentrations directly. And the projection-based approach is going to say, I'm going to apply to each RO bank a dimension reduction model. So basically a multiple linear regression model to each RO bank. And that model, rather than doing a specific output, is going to capture variability, because not all variability in the RO is going to be directly related to NDMA. So we try to do this dimension reduction approach and the correlation approach to compare which one is best for a given modeling application. So the models that we looked at, the first off is, how are we benchmarking this? How do we know our model is doing well? Well, based on the data that we're currently using, we're going to use the NDMA that was measured 30 hours ago. So if you looked at how highly correlated each of our data points are, up to about 30 hours, the NDMA measurement that you took is going to be a really good proxy for what the status quo is. And this can lead to a problem in model building called data leakage. So we're trying to go back as far as when you consider lab time to get my NDMA concentration, right? This serves as a proxy in both of those. So the NDMA measured 30 hours ago. And if we think about how Orange County is currently operating, which is the maximum historical NDMA that was observed. So we're going to be using that one for our energy simulation. And then we did a spectrum of different models. We used a whole range of different hyperparameters. And so for each prediction, we optimized for those hyperparameters, and all of that detail is going to be available in the manuscript that we're going to be publishing on this work very soon. So I'm not going to go into deep detail there. The only other caveat that I will add is that for the model training bit, we trained on all of the data except for data that was 30 hours prior to or after an individual observation. And the individual observation served as a test set. So basically we ended up retraining 162 times for every possible observation, excluding the data that is auto-correlated to that point. So for those machine learning nerds out there that were curious. All right, so big picture, on the top plot there, we have our absolute model testing error, and we have all of our models along the side, with the red being the results from using MRMR as a dimension reduction approach, and the blue being PCA. So the lag model, that is assuming the last known NDMA value, and that's kind of the value, the median value we're trying to beat here. And support vector machines using a PCA reduction approach was the best. It did not have any very extreme outliers. Those are those dots that you see above on the top of that plot there. But you'll also notice that in some cases, there wasn't a big difference between the dimension reduction approaches. That demonstrates that some models are just really good at natively doing some types of dimension reduction. But some models, right, like neural networks, were very responsive to the differences between those two, which could show that, one, we're kind of in a data limited environment. 162 may seem like a lot of observations, but in the world of machine learning, it's really not. So that's why we had to do a lot of adjustments to our procedures to try to account for these smaller data sets and the smaller hyperparameter sets. But at the end of the day, neural networks just have a lot of internal parameters, even the smallest ones that we're working with. So we selected support vector machines using PCA, and that's the graphic that we have going on the bottom there. And we can see it generally does capture those peaks and valleys. There's sometimes it under, sometimes it overestimates, but it does a pretty good job at estimating NDMA post-RO. All right, so we have our NDMA soft sensor. What do we do with it? Or what does this mean for energy usage, right? Which, thinking back to our NAWI pipe parity metric, was the objective of this work. So I'm going to show you here what the projected energy savings could be, or the reduction in UV dose if we use the soft sensor. So we have UV dose on the y-axis. This is calculated based on the known relationship between NDMA log removal and UV dose. We are going to be estimating the UV dose with a very strict NDMA limit of 0.69 nanograms per liter. This is what the California Water Board requires for discharge to potable reuse systems, even though in this case we're using a an indirect system that goes down to 10. So this is just for simulation of a worst case scenario. And this very top line is what the UV dose needs to be in order to treat the max historical NDMA concentration. So it needs to be about 1,800 millijoules per centimeter squared all the time, right? So anything below that line means we can estimate some energy savings. So the black dots, those are going to be what the measured NDMA was and the expected removal to achieve that. The blue is going to be our model predicted results. So that was what you saw on the previous slide. And because sometimes we underestimated, we're also going to be applying some safety factors. So a moderate safety factor in yellow is going to be a 95% confidence interval applied to the prediction. And the red is the most conservative safety factor. So that's taking what was the maximum model error that we saw, and we're going to add that to our observation. So here are those results. First big finding I want to show is that even under our really conservative safety factor, we're still below that UV dose, assuming the worst case, right? So that means that we are generating some energy savings by using this model. By using the moderate safety factor, for most cases, we are still above what is required, right? Whereas if we just use the model output, it isn't as consistent. So if we summarize this across the entire study period and look at our UV dose reduction and the time in compliance, we can see that that direct predicted value, we could get a dose reduction of up to 30%. So 30% from that about 1,800 millijoules per centimeter squared. But we only get about 57% time meeting that 0.69 nanogram per liter limit. Once we apply our that moderate safety factor, though, we still get we are considering significant energy savings, so significant reduction in UV dose over time of about 21% and 96% of time in compliance. Obviously, if we want 100%, right, we have to assume what the maximum model error was. So that gives us 13. May or may not be worth the lift, depending on the UV bill for a particular utility. But no matter what, in all of these simulations, we are seeing some form of energy savings. So what's next? Unfortunately, at OCWD, NDMA actually is not the limiting factor for UV. We found this out after we did our simulation study, where we have to cap it off at about 500 millijoules per centimeter squared for 1,4-dioxane. So we still get about 19% energy savings there, but don't quite meet the 20% pipe parity metric we were looking for. So we are actually looking at Las Virgenes Water District and replicating this in phase 2 at Las Virgenes. So we're currently collecting data there where they are more limited by NDMA in their UV treatment. And this also opens up the door for a couple of other studies where we can think about not just do we see the same model results at a new facility, right? Given how unique data sets are and how unique machine learning is, but also do we see that we can have knowledge transfer between these two systems, right? And that is a big question, is how much information from one system to another can you transfer? Because if we can do that, then as all of these small scale systems come online within the next 10 years, we can begin to have some semblance of startup data, right, or startup information for these smaller systems as they collect more data. And so with that, I am going to close out my presentation, and I am going to open up for Kyle's closeout fairly quickly. Scott, I see you're hopping on. I know I got 10 minutes left.
You're fine. Great. Keep going.
Yeah. I'm just going to really quickly hop into the acknowledgements. So for the PCA work, obviously, our utility partner, Las Virgenes, and the support team from Carollo and Las Virgenes, we'd like to thank. And for NDMA, same thing. Orange County has been great with supporting this work, as well as the folks at Carollo, who are the NDMA experts at us being able to figure this out. So thank you very much. Here is Taylor and my contact information, and we are also here for your questions.
Great. Thanks, Kate, and thanks, Taylor. Those were fantastic presentations. I really enjoyed those. Both of you have had a chance to keep track of some of the questions that were coming in the chat, but we'll start out with the first one, Taylor, which I think you kind of addressed a little bit of, from Chris Velez, who is actually, by the way, one of our task area leads with NAWI, and he says that most models require some tuning can you comment on what it takes to tune the model? So you had described a little bit of that kind of towards the end about how you need to do some tuning, but not necessarily what it
Yeah,
took to do that.
Yeah, so for the long term, yeah, I talked a little bit about this, what we played around with on the long term model. For the detrending models themselves, like the K-nearest neighbors and random forest, those ones were all tuned by tenfold cross validation to find optimal tuning parameters to for to optimize root mean square error. And then for the principal component analysis, we selected the number of components based on retaining 80% or components that explain at least 80% of variability in the data. So that's how we tune those.
So yeah, so you use a statistical approach to be able to determine which variables might need to be tuned and which wouldn't. Got it. Okay. I think hopefully that answers your question, Chris. I'm going to go on to one that was a little bit longer, and I think it's for you, Taylor. It said, given that there are mechanistic models for fouling, can you speed up training the model by using the mechanistic model with fitting parameters as the expected form? I'll start out with that part of it, and then I guess we can hit a second one. Is would this reduce your data requirements for training as part of that?
That's a good question. Yeah, so the data requirements are interesting because, you know, I guess based like our model, for example, had a couple stages to it, and so we needed at least ideally thousands of observations of previous data to fit well, but that varies, depends on what model you're using and what and how many variables you have, pretty much. But yeah, we haven't looked at anything with mechanistic models. I think what we've seen so far with the models that we've been looking at recently that require less data to work with, they've been very nice in the sense that they're very simple, in the sense that we don't have to combine multiple models and multiple sources of data and information. So yeah, we didn't look at that, but the things that we have looked at recently for minimizing the amount of data that we actually need to get a good model has been promising.
And it seemed like you talked a little bit about, for instance, if you didn't have the data, instead of, for instance, going down the mechanistic pathway model, that you kind of briefly mentioned something about the self-starting approach.
Yeah, so there's a self-starting class of models that basically require either very minimal historical data or the one that we've been developing and are about to submit for publication lets you input just basically prior expert knowledge on what you think should happen in the process. So you don't actually need any data, and then it will funnel that through your model and then combine it with data later on. So there are ways of doing that that will kind of eliminate the need for tons of historical data. But right, if you have lots of historical data, it's easier to work with generally.
But perhaps even a combination of a mechanistic model and self-starter or something like that would be useful in these cases. I don't know.
Yeah,
Kate, do you have any thoughts on this?
For sure. Yeah.
Yeah. Kate, any thoughts on that from your perspective?
I think the hybrid approach is always incredibly helpful when that information is available. I think a couple of things is that when we have run some studies, right, where we do the hybrid approach with the mechanistic model, we find that the mechanistic component is not accounting for as much variability as we think it is. And when we think of all of the work that goes into fitting those mechanistic models, because usually that's a very hands-on process.
Right.
it ends up almost defeating the purpose of doing a data-driven approach, because the data-driven approach can sometimes in simpler systems account for that same variability that the mechanistic model, because remember, the mechanistic model
Right.
is still a very simple model relative to some of these approaches. And
Right.
so the benefit of the mechanistic model when it's available is stability, right? You don't see the types of outlandish predictions that sometimes you can, especially if you have a machine learning model with a lot of parameters that you might not have tuned to a specific range. So we see that that is helpful. As Chris Valet just threw into the chat, also, the mechanistic model is an invaluable benchmark, even if it isn't actually being used in the status quo,
Right.
knowing that that is what the model can perform with, because it's much easier to program, because it is much more stable, and it's much more interpretable. So you talk about communicating that to operations staff. There's a lot of benefits to mechanistic modeling that should be used, but recognizing not all situations have that available. It really just depends on what your objective is. So back to the idea for these types of projects, are you defining the problem appropriately with specific metrics? And then you can go from there, rather than letting the project take you to the objective.
Good point. Good point. I like that. I like that answer. I think captured a lot of what we're talking about here. Okay, so going back, I see some of these. Adam's asked a few questions. Eric has asked a few other questions. I'm not sure if they've all been answered. I know that it looked like one that I was looking at. Eric asked if he's basically, isn't the true measure of your model to compare what it communicates about downstream RO performance to the actual RO performance? So that's back to you, Taylor, in terms of kind of getting at the you have pretreatment that you were looking at as an explanatory variable for the rest, but he's going back to, well, don't you really want to look at the true RO performance as kind of the indicator in all this? And so I don't know if you have any thoughts on Eric's.
If your main, I guess our main goal as that project was not to look at the RO really. And so if your main goal is to specifically be looking at making sure that everything is doing well for the RO, then yeah, you definitely want to compare that. That just wasn't something that was really part of what our main focus was for the project, so we didn't look at it.
Yeah. Kate?
I'll add on there, actually. So we did try to look at the RO data for fault detection way back in the very beginning of the project. However, like I mentioned, these RO systems have so many variables and so many data streams. Really talking to operations staff over the course of a year and saying, is this little one here, is this a fault? Did this occur?
Right.
It was not, we could not get consistent results. So when we talk about doing this process of validating our method on a data set, a year later, where we know there's in control and out of control conditions, that wasn't feasible right now on the RO unit. So for a proof of concept of these are what we're monitoring, this is how we can detrend it, and the PCA-based dimension reduction approach, I think we demonstrated that it worked pretty well. And we saw the benefit also of the PCA-based approach and the process control piece. So Eric, I agree that if we're really targeting what's going on in RO performance, yes, we would love to directly use that RO data. For this case, some of the water quality changes that we want to be able to understand how they're going to impact RO, we think that this could also be an informative tool for that, in addition to the UV or the UFMF, which is pretty standard pre-treatment for RO systems as well. So thinking of RO more holistically was kind of the conversation we had with NAWI with this project, right? So mine's really, in the end, the energy savings are in the UV unit, not necessarily the RO, but the RO produces so much data and is so critical. We see a lot of different ways to incorporate data-driven monitoring and fault detection.
Yeah, good. And there's Adam just kind of put another kind of comment, I guess, on that, where there is value in looking at, for instance, specific flux and other RO variables that we look at. I wanted to hit on another one though, that this is for you, Kate, that kind of came up in the discussion there, and that's your result of the 13% using the 100% accuracy, or knowing that you're going to be able to predict all issues with that on the UV side. Is that, is that enough? Or, I know you said that your threshold was 20% that you were kind of shooting for. Maybe 13% could be enough in terms of savings for using an approach like that. Have you gone through any kind of costing assessment of that?
So in previous projects where I worked with full-scale utilities, a benefit of less than 20%, when you start talking about the steps it's going to take to truly get to implementation, right? So first off, we're going to talk about having to need much more frequent NDMA sampling, right? As a portion of control, right? So we have the analytical burden on top of that. We have to do a ton of training for operations staff, right? To understand what this new control strategy is, right? On top of doing all the control strategy modifications. Right. And so suddenly you're talking about a lot of time and material and it goes from being, now the idea of is 10% enough, really is 20% enough. Right. So I think looking at it in the long term, it can be beneficial. I think utilities like Orange County that have a lot of these resources readily available see more benefit than the smaller utilities. But I think when you start, putting up all the person hours that would need to go into that deployment phase for a project like this, I don't believe that 13% would be enough to merit it.
Yeah, and as we all know, a lot of the operators they're more of the opinion that 100% confidence is priceless, and so maybe it's not worth it to try to fine tune those costs at that under 20% scale, and it's just worth just having that confidence by not trying to vary that and tune that in to be as optimal as possible for some moderate cost savings.
Yeah.
Well, Adam, interesting question. He asks at the end here, would those added costs not be transitory?
I would say that you're not wrong, right? It's
right.
I think if utilities were further along in their digital utility journeys, then I mean, yes, all of the effort that would be put into this would benefit long term for not just this project, but future projects. So it really would be an investment that would not just yield the 13%, but much further down the line. But then that becomes a much bigger conversation than just this one project, right? So we talk about the nuances of this particular data stream and this. No, now we're talking about a much larger data management strategy and control system strategy internal to Orange County. That I think it's, if this project can say, Orange County, this is worth your time, then great. But now we're talking about at least a year or two delay for them to spin up those types of large system-wide projects. And I think that's the whole purpose of these NAWI projects, right? In this particular project is showing, yes, you can have those benefits to give, the people that are sitting at the table, the justification to say this is something we should focus on long-term.
Yeah. Good. Again, wonderful discussion. Great research. I really appreciate both of you sharing this with us. And I could keep going and asking question after question because I'm really curious about this, but we're at time. And so again, appreciate both of you presenting today. Thank you so much. And again, thanks for everyone for joining us. Have a good one.
Thank you.
Bye.